the magnitude of phasor is going to be square root of a square plus b square. Okay, that's just Pythagoras theorem. Okay, so this all should be pretty clear. So now I'm going to do one bit of this. There's no hand waving here. Okay, but now I'm going to do some hand waving, and the hand waving I'm going to do is to give you the intuitive meaning of j, or reconcile the meaning of j with what. Let's say I have a unit vector over here, and this is going to be 1. Okay, so I apply j to it, and I get this one, which is going to be j1. Okay, what happens if I do one more rotation on an operator again? I'll get -1. So I get -1 equals j times 1. And let's say I call that j square 1. Okay, so now I'm going to do the funny thing. I'm going to take the square root of an operator. Yeah?
I think there is a mistake in the first two equations.
Yeah?
A equals cosine of theta.
Yeah?
That shouldn't be A over the magnitude.
Oh, that's right, A over magnitude, that's right. So I'm cos theta, you're right. Yes, it is, you're right. So let's call this magnitude equals m. So A over m is going to be cos theta. Thank you. Okay. Yes, that's right. Yeah, I'm kind of switching between unit and not unit and making a mistake here. So yes, that is correct. Thanks. So let's come back to this. So here we're going to apply j. I'm going to do this funny thing. I'm going to take the square root of an operator. So what does the square root of an operator kind of mean? It just means do half the operations. Okay. So if I do 1, 2 steps, or 3 steps, or 4 steps, let's say square root of that is 2 steps, obviously. So I can imagine that I can do that. So I get this square root of -1 equals j. Okay. Oh, great. So I got what I wanted. You know, j is this imaginary number, and it is hand wavy, but it's kind of giving you the reconciling the notion of j as an operator and square root of -1. So what it's sort of saying, if you can think about it, is every time you see square root of -1, it's like rotation by pi by 2 counterclockwise to the of the associated magnitude. In this case, it's going to be b that's being rotated 90 degrees, okay, or pi by 2. Okay, so that's the way we can reconcile these two things together. Okay, so as it turns out, once we start getting into this in a little bit more detail, we start doing Fourier analysis, the meaning of j kind of disappears completely. We just have some couple of formulae, and we know what the formulae mean. Or actually, we don't even know what they mean, we know what they do. So we can just kind of plug and chug, you know, and not have to worry about what j means. But for those of you still wondering, hopefully this gives some insight into what's going on here. Yeah?
What would you say is the relationship between j and I?
J is I in electrical engineering. In math, we use I, and electrical engineering, we use J because I stands for current. Okay, and it gets, once you start doing circuit analysis and so on, it gets complicated, and I'm following the electrical engineering convention of using J. But yeah, I is taken, so you have to use J. But yes, I is the same thing. I actually started writing the chapter with I, and I had to go back and change everything from I to J because I ran into some troubles later on. Okay, any questions about this? Okay, so this is again all hopefully stuff you've seen before. Now I'm going to take one step further and talk about Euler's formula, because so far you haven't needed Euler's formula, you haven't needed anything. You know two things. You know what a sinusoid is, you know what a complex number is. And now we're going to put the two together. Okay, we're going to take this world of sinusoids and phasors and the world of complex numbers, and we kind of do the two together, relying on this over here. So we know that this is, if you view this as a phasor that's rotating like this, then we have this angle theta, and then it's going to have some a plus jb, which is changing all over the time. So Euler has this beautiful formula, and it says basically e to the power j theta equals cos theta plus j sine theta. Okay, and now just like we had the problem before, e to the power matrix, now I'm stretching your imagination even more, saying e to the power complex number. What does it mean? It doesn't mean anything. It's just convenient. What is it? How do we prove it, by the way? Okay, the way you prove it is to take the Taylor expansion of E and of cos theta and of sin theta, and if you put the two series together, you'll find that the two series sum up to be E. Okay, it's very simple actually. If you know the Taylor expansion for cos theta and j sin theta, what will happen is all the j squared terms will become negative, and all the and so anyway, you try it out, you'll see how it works. So we can prove it, we can use it, we don't have to know what it means. Okay, but this is the formula that you need to remember. It's one, and it when theta equals pi, then we get e to the power j pi equals what's cos pi is going to be 0, right? What am I doing? Yeah, minus 1. The sine is 0 and cos. Okay, minus 1 plus j times 0. Okay, so we get e to the j pi plus 1 equals 0. And this formula has been called the most beautiful formula in math. Okay, it's got all the magic numbers, j, pi, e, 0 and 1. Okay, and it's all related together. What does it mean? Who knows? I mean, I don't know what it means either. But there is this wonderful book, I think I have a reference to it in the end, called Dr. Euler's Magical Formula or something like that. And it's this by a retired professor of electrical engineering called Nahin. And it's really a beautiful book, one of the nicest mathematical books you'll ever read. It's all about this formula and everything that comes out of it. So anyway, so people did a poll, I guess some bored mathematicians sat around and said, what's the most beautiful formula? And this is supposed to be the most beautiful formula in math. So if you're in the business of making t-shirts, you can certainly make one like this, e to the j pi plus 1 equals 0, and you can put something else in the back. This is the mathematician's answer to E equals mc squared, but their E's are different from our E's. Okay, so let me do a couple of examples just to make this clear, and then we'll go and relate this to sinusoids. Okay, so maybe I should just solve the homework example. So what did we have here? I said represent e to the j pi by 4 plus e to the power j pi by 4 plus e to the power j pi by 2. So here we have two of these e raised to this complex quantity. So say you just ignore the e, and we'll just say it's going to be cos pi by 4 plus j sine pi by 4 plus cos pi by 2 plus j sine pi by 2. And then if you simplify that, you'll get basically root 2 over 2 plus j 1 plus root 2 over 2, or if you want to expand that, it's 0.707 plus 1.707 j. Okay, so we have the nice a plus jb form, okay, as the sum of two complex exponentials over here. Okay, and I hope all of you got it right. And again, hope the idea of giving you this exercise was to kind of demystify the whole notion of raising e to the complex power. It's not that hard. You just get a plus jb at the end of it. Okay. All right. So let me just move on. So I want to just talk a little bit about this over here, and note that when we talk about a phasor rotating, we actually only need two things about it. We need to know its magnitude. Okay, how big is it? And second, what angle is it making at a particular point in time? Okay, so if you know the angle at that point in time, or we know the angular velocity and the time, either way we know the angle. So we kind of know exactly where it is. We know this part. Okay, so basically we know where it is. So we need to know, either we need to know theta and m, or omega and t and m. Okay. For now, let's assume that m is 1. Okay, just for simplicity, it's a unit. Then all we need to know basically is theta. Okay, so I could tell you phasor is theta, and you know where it is. Okay. However, what we do is that for notation, we don't say theta, we say e to the j theta. Okay. So in some sense, the E and the J are just extra. You don't really need it, okay? Because if I told you theta, what it is, I could easily compute, the A is m cos theta, B is m sin theta, right? So I know the A and B values. But because of Euler's formula, I can do that because e to the j theta is going to be given by cos theta plus j sin theta. So we're kind of getting the cos theta and sin theta, quote unquote, for free. So if I say m, to be more precise, if I say m e theta, then it's going to be m cos theta plus j m sin theta. So then I'm getting everything. So if I just say m e to the j theta, I'm getting these two, and the plus is basically notation. It doesn't mean anything. I can't really add the two together other than the vector sense. Okay, these are, one is a real, one is a complex. I can't add them. Or you can equally well think of them as being a comma, and you can even say it's like this, right? It's m cos theta, a tuple, m sin theta, and just notationally I'm going to represent it with a plus in between. But these are, I can't add them. One is apples, one is oranges. You can't really add the two, but you just, again, convention is we write it like that. So Euler's formula basically allows us to relate phasors to complex numbers. Okay, that's what is happening over here. This is just a standard complex number, right? I'm not doing anything special over here. And this over here, theta m and omega tm, are sinusoids. This is all coming from the world of sinusoids. Theta is the angular velocity, is the angle, is the phase angle over here, okay? And omega t is the angular velocity. So the world of sinusoids and the world of complex numbers are brought together by Euler's formula, okay? Because it very clearly shows you that this theta is now represented in this form, cos plus sine, where j comes in right there. So that's why Euler's formula is so important. It brings these worlds together. So this gives us the necessary formulae to compute from one world to the other world. So if I give you the magnitudes, if I just say a plus jb, okay, then I can say magnitude m equals square root of a square plus b square, and theta, which is what I want over there, is going to be tan inverse of, is it b over a or a over b? It's b over a. Right, b over a, I think, yeah. No. Okay. Let me look up my notes instead of making it up. I can't think while I teach. I can only talk. Okay. Let's see. It's a b over a. Yeah, it is b over a. Okay. And if I have the notation m e to the j theta, then I get a equals m cos theta and b equals m sin theta. So I can go from one world to the other, okay, a plus jb world to the m theta world, and from the m theta world to the a plus jb world, okay, and that's kind of, you're getting it for free. And so that allows us to solve the next homework problem, which was, I believe, I'm going to switch again, it was, I think, 4 plus j3. So what is 4 plus j3? We just plug it, chug, you get 5 e to the power j tan inverse 3 over 4. Okay, and that's the answer. And if you want to simplify that, I think I did do that with my calculator. It's, I guess I did not. Whatever it is, it's some number of, it's, yeah. So that's the answer. If you want, you can simplify this to some number of radians. It'll be in radians, okay. Tan inverse in the radian sense. Okay. So any questions about this? Okay, so that's good. We can move on. Right. The other thing I want to talk about is, so we talked about omega being the angular frequency over here. So I said that theta equals omega t, and this is the angular frequency. Now, in doing so, we're assuming that omega, that the rotation is going to be counterclockwise. Okay, what if the rotation is clockwise? Well, if the rotation is clockwise, we still get the same sinusoidal out of it. Okay, and for convention, we call that omega rotating clockwise is going to be a negative frequency. Again, it doesn't mean that it's actually negative, okay? Because when you say I've oscillated at negative 30 hertz, you kind of say, what does that mean? Nothing. It just means that in the underlying mathematical notation, I'm assuming that there's a phasor rotating clockwise rather than anti-clockwise, okay? And in most cases, it doesn't matter, okay? Because cos of negative 2 pi is going to be cos of 2 pi, okay? Sine is going to be the same thing. For the negative angles, it's going to be for double angles, it's going to be the same. But obviously, for sine minus pi, it makes a difference whether it's plus pi or minus pi. But anyway, that's the meaning of negative. Again, it's a notational convenience that we need to worry about. So there's the example I have. So I have a clock, an actual clock, and I have a second hand, okay, and it's going around like this, right? So what's the angular frequency of the second hand? Okay, if you have a watch or something, you're kind of watching it, it's like this. What's the angular frequency? So, okay, so since it's in the text, I'll just tell you. So what's the period, right? We just started the period. The period is going to be 60 seconds, okay? And that's equal to t. And now we just use the formula that omega equals 2 pi by t, so it's going to be 2 pi over 60, and this is going to be pi over 30, okay, radians per second, except you're going to make it negative because it's going to be going clockwise. It's a clock, right? So it's negative pi by 30 radians per second is the answer. So we can actually compute the quote-unquote constant velocity of your second hand using this way. So, though you've just seen a fairly straightforward introduction to this notion of a phasor as being represented as m e to the j theta, again, you have to think of this as just being the tuple m theta. Already you have enough to understand something quite important, both about how information is sent and about the limits to how much information can be sent. So I'll talk about that right here. So let's call keying is basically how do we send a 0 or a 1 on a communication line. Oops. So I have a link between two nodes and I'm sending a sinusoid on it, okay? And I want to send a 0 or a 1. How do I do it, okay? So the first way of doing it is called amplitude keying, or amplitude shift keying. Or ASK is what people also use as the acronym for it. And all it says is that I'm going to send the sinusoid like this, and then to send a 0 and to send a 1, I'll go like that. Okay? And that's a 0, that's a 1. And we can mathematically see it as being basically m1 theta and m2 theta. So we are continuing the sinusoid. It's not really changing. It's the same phasor, but except that we have, if you think about it this way, in this sense, I basically got a phasor like this, that's m1, and then I have another phasor like that, which is going to be, and this one is m2. So I really should be drawing two circles like this. So if I draw this this two lines like this, one here and one there, and I call this 0 and I call this 1, it should become clear what's going on. This picture really represents in one single picture the fact that I'm sending two different magnitudes, okay? And in fact, the way that communication engineers represent it is even simpler. They just draw a circle like this and they draw two x's and they draw m1, m2, and this is amplitude shift keying, okay? As simple as that. So I've gone from this picture, which is the sinusoidal world, into the phasor world, into an even simpler representation, but this and this are the same thing. Okay, this and this are the same thing. So everybody get it? Right? So when you see a picture like this, it means that. Okay? That's what you learned in this lecture, how to go from this picture to this picture. Okay. So, which is not bad. Okay, it's not bad. Okay, any questions about this? So, the second thing is what's called frequency shift keying. And frequency shift keying, what we have is basically we have m theta 1 and m theta 2. So we have two different frequencies, okay? And so we're going to have in the sinusoidal world, we're going to go the same magnitude. This could be 1, and then we go like that. And then this is you know, 0, 1, 0 or a 1, 0, 1 or whatever, but you know, we have basically one frequency here, 1 here, and 0 here. And we can't represent that using this picture here because, you know, this is assuming a constant, but we'd have basically, we would say here's the two different frequencies. So this is frequency 1, frequency 2, and then we have over here some magnitude. So these are the two different phasors, the different frequencies, okay, or different omegas if you want to be more precise. This is omega 1, this is omega 2. Okay, so this is how we send zeros and ones. And then the third thing is called phase shift keying. Or it's called PSK. And here what we do is that, it's kind of funny, we start with this thing over here, and then at this point we're going to change the phase. So normally we'd be going down like this, okay, and then going up like that. Let's say we just move it over like so, okay, then we're going to kind of go up like this again. So the dotted line represents where you would be if you didn't change the phase. So and here this is 0 and this is 1. And then if you change the phase again, what will happen is that you might end up with this, and then basically you continue down from here. So there are these sort of breaks, if you will, between the two phases, and this would be a 0 again. I think I got that right. So over here, mathematically, it's easier to see as basically m theta, and then we'll have a phase of the other one is m. So I'm going to call this theta 1, theta 2, and then theta 2 equals theta 1 plus some shift, okay? So I'll just write that shift. Okay. And so it's a constant shift, okay? So the angles, if I know m1 theta 1, and so if I know theta 1, I sort of know what the shift is, okay? So while doing this, it's worth kind of figuring out a few details, and let's go through that. So with amplitude shift keying, I'm going to change the amplitude. What happens if I get noise on the line? Basically, these things are going to get corrupted, okay? So it's not going to look like that at all. It's going to be kind of jaggy going up and jaggy going down, and jaggy going up and down over here. And sometimes what will happen is that this will go like this, okay? And so it'll look like a 1, even though it wasn't a 1, because the noise is distorting the signal. And we'll think it's a 1 even though it's a 0, okay? Because we are looking for a particular amplitude. It looks like a 1. And so amplitude shift keying is susceptible to noise, okay, because noise adds this thing. And in the world of analog communication, not digital communication, we're not sending zeros and ones. When we're sending voice signals, for example, this corresponds to amplitude modulation, which is AM radio, for example. AM radio uses amplitude modulation. So keying means I'm sending 0 and 1. Modulation means I'm sending a continuous signal, okay? So in AM radio, as you heard probably, or maybe not, it's noisy. Okay? There's a lot of noise all the time, because the signal is susceptible to noise. Now this, over here, what we're doing is that we're going to have essentially two reference frequencies, one at the sender, one at the receiver, and these frequencies are known. Okay, they need to know upfront, these are my frequencies, which actually, there are going to be some center frequencies and some variation around the center frequency. But those are the known frequencies. And what happens is that the detector is going to be looking at, is this frequency or is it that frequency? It matches the two, and it says, oh yeah, I got something at this frequency, it must be a 0. I got at this frequency, it's a 1. So I won't go into how that's done, that's communications. But at any rate, the important thing is that noise does not affect frequencies. Okay, so if I change from, let's say, 2.432 gigahertz to 2.537 gigahertz or megahertz, so like Wi-Fi is at typically at 2.437 is one of the center frequencies, 2.5 something, 524, I guess, something like that. This is other center frequency. Noise is just making this jaggier, right? So these guys are getting jaggy, okay? But that's not going to be changing the frequency. So you can see it's immune to noise, okay? So that's why FM radio sounds clean compared to AM radio. Okay, FM radio sounds clean because the noise cannot change the frequency, and all we care about is frequency, even if it's noisy. Okay, so we rarely have noise in FM, and in fact, AM is, nobody uses AM anymore for that reason. Okay, it's frequency shift key. Now, remember, however, that both ends need to have the frequencies known. What is the 0 frequency or the 1 frequency? And they need to have what's called local oscillators that are very, very precise. So the two local oscillators need to be very matched, because if you make a mistake and the 1 becomes a 0 and 0 becomes a 1, all the bits are going to be inverted. So it's not a good thing to happen. But it turns out that you can have these self-tuning oscillators which use the received signal to find the thing, and there's some quite a bit of theory and practice to make sure that the oscillators are going to be okay. So this is very widely used. Even more widely used is phase shift keying. Now in phase shift keying, we actually need to know not only the frequency but also the phase angle. In other words, both sides need to start their phasors at the same exact offset and kind of going together, because then they'll be able to figure out that something was out of phase. Okay? So there'll be a training duration in the beginning of the signal where both sides make, okay, for example, this transmitter is going to say, I'm going to send you 1,000 zeros one after the other. Adjust the tuning of your phase so that your phasor is in line with me, because I'm going to send you everything with this phase. Once you're in line, now any change in phase is going to be a 1. Okay, so that's how we do the training. And so once we do this, we need good oscillator, plus we need training. And if you do those two things, then we can detect phase shifting, and this allows us to be quite good. So let me show you. So let me draw the angle picture for this. So here is my m theta 1, and because it's a constant shift, I can just draw. If I imagine a circle like this, right? I'm going to just draw another one over here, and that over here is my phase shift. Okay, that's the shift over here, not theta, but that's the shift over here. Okay, so I'm basically showing that I have got over here one magnitude and two phasors, one over here, one over there. Now the standard way of doing phasors, I'll show you what's the standard way of doing it. I'll just draw these pictures. Am I going off the edge? Okay, I'll go back here. Let me draw some standard pictures. These are what I call constellation diagrams, and this is a standard constellation diagram, and this is called a binary phase shift keying, and we have two phases that are 180 degrees out of phase. Okay, we have two phasors, we're 180 degrees out of phase. So in the beginning, we're going to lock one phasor up to the center, and then whenever we detect there's been a phase shift, then we say, okay, I got a 1 or I got a 0, whatever. So you get either a 0 or a 1. But I can be cleverer than that. I can do this. I can do 1, 2, 3, 4. So now I'm detecting 90-degree shifts. Okay, so I'm saying I'm here, 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 and this is called binary phase shift keying, BPSK. This is called quadrature phase shift keying, QPSK. And so now when I detect something, I'm getting 2 bits out of it. So one signal detection is giving me 2 bits of information. So I get 2 bits, and each of these is called a symbol. And we'll study this more when you do information theory, but on every symbol we're getting 2 bits, so it's called 2 bits per symbol. Okay, and that's nice. I just double the data rate, and I can do better. I can do 8 even, so I can do 1, 2, 3, 4. So now it looks like some stars in the sky. That's why it's called a constellation. Okay, it looks like some constellation of stars. And now I'm getting 3 bits per symbol. Okay, getting 3 bits per symbol. So that looks good. But I can do better than that. I can mix phase shift keying, and I can do amplitude modulation too. So I can do something like this. I get 4 from the first magnitude, and I can do 4 more from the second magnitude, but I'm going to keep them like so. Okay? So I'm getting 8, but they're all in different magnitudes. So I can use the change in magnitude and the change in phase to detect things. And so this is actually what's called 8 QAM, 8 quadrature amplitude modulation, and you can get 16 QAM, and you can even do 64 QAM, where 64 QAM means it has 64 different points. So each detection is going to give me 5 bits. Okay, 5 bits of detection, because 2 to the 5 is it 5 or 6? 6, sorry. I'm getting 6 bits out of just one symbol. Okay, so you can ask yourself the question, okay, this is great. Why not have, 32 or 64,000 QAM? You have 64,000 different positions, and I'm going to get, 16 different bits at the same time. So what happens is when these points get too close to each other, if I have really got a constellation kind of thing and have stars all over the place, okay, noise can kind of bring these two together, and then I'm getting bits in error. Okay, and so one of the most fundamental discoveries of communications theory or modern mathematics or whatever is to characterize this exactly. Okay, how far can we go? Can we do 32? Can we do 64? Can we do 128? At what point do we run out of bits? And the answer is depends how close things are and what the noise is. Remember, the noise is going to distort stuff. So the more noise there is, the wider space these things need to be, because otherwise I can't detect them. And Shannon, who invented information theory, was able to characterize this mathematically. He's able to show exactly how much noise you can tolerate. And that tells us the limits to which you can go with these constellations. By the way, 16 QAM is widely used, and if you are interested, you can go look up Wi-Fi 802.11, go look up on Wikipedia and read up the section on Wi-Fi, what's used for keying, and you'll find exactly a constellation diagram showing you what all the phasors are being used in Wi-Fi. Okay, I think it's 16 QAM is what they use. And so now, you can see you can go from Euler's formula and this fairly simple thing to what's used in practice today. This is exactly what people use in practice today. 16 QAM. Once you know what a constellation diagram is supposed to mean, these are just a bunch of phasors with m and theta associated with them. You know how to read them. You can figure out what's going on. So that's nice. I'm going to end with just a couple of useful things to have in your pocket, at least for later on, which still builds an Euler's formula, which is going sort of the other way. So we know that, so first of all, we should say that cos of minus theta equals cos theta. Okay, and sine of minus theta equals minus sine theta. Why is that? So let's say we have this angle here. This is theta. Negative theta is going to be like this. So this this distance over here, it doesn't matter whether it's theta or minus theta. It's going to be the same distance over here. So obviously cos theta is going to be cos minus theta, whereas sine will change direction. So sine changes sine. It's a bad mathematical pun, but you get sine minus theta is minus sine theta. Therefore, e to the j theta is equal to cos theta plus j sine theta. E to the minus j theta is equal to cos theta minus j sine theta, which means that e to the j theta plus e to the minus j theta equals 2 cos theta, which means you can just say e to the j theta plus e to the minus j theta by 2 is cos theta. And so this is a good thing to remember. Okay, e to the j theta plus, so you just, if you want cos theta, you can just take this. So what this means is that if I give you a trigonometric function cos theta, which is a pure trigonometric function, I can represent it as a complex exponential. It's called a complex exponential. And similarly, we can show that sine theta equals 1 over 2j, and it's going to be e to the j theta minus e to the minus j theta. Okay, and this is the other kind of useful thing to have, how to represent a pure sinusoidal, a pure cosine as a complex exponential. When we study the what does e to the j theta look like, and I'll actually show you some pictures, I think it will become clearer how we get this kind of nice thing where on the right hand side we have a real number, on the left hand side we have complex, right? But somehow it works out. I'll show you how that works. Okay, so I'm going to stop here, and then next time we'll continue with the next thing, which is convolution. Okay, we'll do convolution, discrete and continuous, and so on. Okay.